Good morning all. Today we are going to discuss about third unit, that is recurrence relations. So in third unit we are going to discuss about what is a recurrence relation, what are their applications, how to solve linear recurrence relations, what are generating functions, what is principle of inclusion exclusion, what are their applications, and divide and conquer algorithm. All these concepts will be discussed in third unit. So first we will see what is a recurrence relation. So a recurrence relation is nothing but expressing a sequence in terms of one or more its previous sequences. For example, take an. If you write an equal an minus 1 plus an minus 2. That means we are expressing an in terms of its previous terms. So it is nothing but a recurrence relation. So we can define a recurrence relation for a sequence an as the equation that expresses sequence an in terms of one or more its previous terms. So that is nothing but a recurrence relation. Then what is a solution? A sequence is said to be a solution for a recurrence relation if its terms satisfy the recurrence relation. Here these are some examples for recurrence relations. See, an equal 1 plus 2 into an minus 1 for n greater than or equal to 1. Because for already we take a1. You see, already we taken as a1 equal to 1. That as initial condition is there, we are starting with 2. So if you take n equal to 2, then we will get 1 plus 2a1. That is 1 plus 2. That is 3. So second term will be like this. So if you substitute n equal 2, 3, etc. in this equation, the terms will be 1, 3, 7, 15, 31, 63, etc. All these are some of the terms of the given recurrence relation. Take one more example. An equal 3 into an minus 1 plus a into n minus 2 for n greater than or equal to 2. Because here already initial condition is given, that is a naught equal to 1 and a1 equal to 2. So if you start substituting from n equal 2, 3 and so on, the terms in the sequence will be 1, 2 are the initial terms. Next terms we will obtain will be 9, 33, 126, 477 and etc. All these are examples for recurrence relations. Next, here one recurrence relation is given. An equal 2 into an minus 1 minus an minus 2 for n equal 2, 3, 4 and so on. So here we have to check whether the sequence an equal 3n is a solution for the recurrence relation or not. How can we say that it is a sequence is a solution? If we substitute this term in the recurrence relation and if it satisfies the equation, then we can say that it is a solution. So first consider the equation 2 into an minus 1 minus a into n minus 2. So here we got an as 3n. That's why an minus 1 will be 3 into n minus 1. So 2 into 3 into n minus 1 minus n minus 2 stands for 3 into n minus 2. 3 into n minus 2. So we got 6n minus 6 minus 3n plus 6. Plus 6 minus 6 gets cancelled. 6n minus 3n. We get 3n. So what is 3n? 3n is equivalent to an. So if you substitute an in the given equation, we got the same. Hence we can say that an equal 3n is a solution for the given recurrence relation. Take one more example. Here an is considered as 2an minus 1 minus an minus 2 for n equal 2, 3, 4 and so on. So sequence given is an equal to 5, means constant sequence. So even if you take an minus 1, an minus 2 etc., its value will not change. Now consider the recurrence relation. So 2 into an minus 1 minus an minus 2, that equal 2 into what is an minus 1? An equal 5, constant. That's why an minus 1, an minus 2, anything will be constant only. So 2 into 5 minus 5. So 10 minus 5, that equal to 5. So if you substitute an in the given equation, we got the same thing. Hence we can say that an equal to 5 is a solution for the given recurrence relation. Next, applications. So what are applications of recurrence relation? That means where we are going to apply all these things. So we can use recurrence relations in fields such as finding compound interest, counting rabbits in an Iceland, and determining number of moves in Tower of Hanoi, counting bit strings with certain property. In all these type of problems, we can apply recurrence relations. So see the first problem. In finding compound interest also, we can apply recurrence relations. Problem is, suppose someone deposit $10,000 in a saving account and annual interest, compound interest will be 5%. Then we have to find how much money will be in the account after 30 years. So using recurrence relations, we can solve the problem. See, first Pn is denoting the amount in the account after n years. So account in the after n years means account for the n minus 1 years plus 5% interest for the last year, current year. So it can be expressed as Pn equal to Pn minus 1 plus 0.05 into current year n minus 1th year. Take Pn minus 1 common. So if you take n minus 1 as common, 1 plus 0.05. So we get 1.05 into Pn minus 1. So this is the recurrence relation. So initial condition means initially someone deposited $10,000. So initial amount will be 10,000. Next we have to compute P1, P2, etc. So what is P1? Substitute n equal to 1 here. So we will get 1.05 into P0. Next compute P2. What is P2? P2 stands for 1.05 into P1. So in place of P1, substitute P1 value here. So that equal 1.05 into 1.05 into P0. So it can be expressed as 1.05 whole square into P0. So P2 can be expressed as 1.05 whole square into P0. Similarly P3, it can be expressed as 1.05 into P2. Substitute P2 value here. So we will get 1.05 into 1.505 whole square into P0. So we will get 1.05 whole cube into P0. Continuing like this, for nth term, Pn will be 1.05 into Pn minus 1. That equals 1.05 whole power n into P0. So we have to compute for 30th years. So take n equal 30. So we will get P30 equal 1.05 whole power 30 into 10,000. So that equal 43,219. So we can say that after 30 years amount in the bank account will be $43,219.42. Next problem is counting rabbits in an island. So this problem was defined by a person who is called as Fibonacci. So in the problem, a young pair of rabbits, in both one is male and another is female. So a young pair of rabbits is placed in an island. So a pair of rabbits does not breed until they are 2 months old, and after that each pair of rabbits produce another pair each month. So we have to define a recurrence relation for finding number of pairs of rabbits in the island after n months by assuming that no rabbit ever died. So this is a problem for counting number of rabbits in an island using recurrence relation. So initially one pair of rabbits are there. In first month they cannot breed. So initially reproducing pair is 0, young pair is 1, and so far total pairs is 1. Take the second month. In second month also they cannot reproduce the rabbits. So in second month also reproducing pairs will be 0, young pairs is 1, total pairs is 1. Go for third month. So in case of third month, this pair will produce one pair of rabbits. So in third month, one pair of rabbits were reproduced, young pair is 1. So in third month, total pairs will be 2. Come to fourth month. So in fourth month, this is the original pair and this is the recently born rabbits. As it is in fourth month, they will produce one more pair. So in fourth month, reproducing pair is 1, young pairs is 2 and total pairs is 3. Like that, it will be generated. So for this, we have to write generating recurrence relation. So number of pairs of rabbit after n months. It is denoted by the term Fn. So according to the problem, at the end of the first month, young rabbit doesn't produce any pair of rabbits. So number of pairs by the end of first month will be 1. So we will take F1 equal to 1. Similarly, by the end of second month also, they do not produce any new pair of rabbits. Hence, we will take F2 also 1. So what we have to compute? We have to compute number of pairs after n months. So n month means till n minus 1 month, the number of rabbits will be denoted by Fn minus 1 plus for last one Fn minus 2. Because newborn baby means 2 months before only they will generate. So it will be Fn minus 1 plus Fn minus 2, where initial conditions are F1 equal to 1 and F2 equal to 1, and generating function is defined as Fn equals Fn minus 1 plus Fn minus 2 for n greater than or equal to 3 onwards. So this problem was defined by Fibonacci. So this is used for counting rabbits in an island. Next problem is Tower of Hanoi. So in Tower of Hanoi, problem consisting of 3 pegs mounted on a board together with discs of different size. That means in case of Tower of Hanoi, if you see the diagram, there are 3 pegs, and on first peg we are having disc of different sizes. What we have to do? We have to move each disc from one peg to last peg, one by one. And one more thing is we have to do one by one only. See, initially these discs are placed on the first peg in the order of size with the largest on the bottom. So here we are having 3 pegs, and on first peg we are having disc of different sizes. The rule of the puzzle is disc should be moved one at a time. We should not move all at a time, and they should be moved one by one. One at a time from one peg to another, as long as a disc is never placed on the top of a smaller disc. That means when we are transferring the disc, we should remember that a disc will be never placed on the top of a smaller disc. So what is the goal? Here we will Hn denotes the number of moves required to solve the Tower of Hanoi problem. So for n discs, we have to generate a recurrence relation for the sequence Hn. So this is the Tower of Hanoi problem. 3 pegs will be given. On the first peg, different discs of different sizes are placed. We have to move from one peg to another place, and they have to move one at a time. And condition is that a disc should not be never placed on top of a smaller disc. Using this condition, we have to change. So this is the initial position. Initially 3 pegs are given. On first peg, we are having disc of different sizes. So small one next to, like that, in this way 3 pegs are given. So what you have to do is, we have to transfer these discs into here. So this is the intermediate position. So except the last one, the remaining pegs will be moved, remaining discs will be moved here. This should not be moved, because if you place here, this will be on top of the smaller one, which is not allowed in the room. That's why this should not be moved here. So we are assuming that there are n discs on the peg. So except the last one, the remaining n minus 1 disks will be moved in Hn minus 1 moves. So for moving from this one to peg 2, it requires Hn minus 1 moves. From here to here, we require another Hn minus 1. So Hn minus 1 moves plus Hn minus 1. 2 into Hn minus 1 moves. Plus this should be shifted from here to second peg. So for this, one move is required. So 2 into Hn minus 1 plus 1. Because from here, with n minus 1 moves, disks will be moved here. From here, it requires one more Hn minus 1 moves to move here. So Hn minus 1 plus Hn minus 1. 2 into Hn minus 1. So according to the given condition, this largest disk should be moved to second disk. So for this, it requires one step. So 2 into Hn minus 1 plus 1. That is the recurrence relation for the given problem. This is like that. Hn equal 2 into Hn minus 1 plus 1. So that is the recurrence relation for the given solution. So we can solve using iteration. Hn equal 2 into Hn minus 1 plus 1. Go by using iteration method, Hn minus 1 can be written using its previous terms. That is 2 into Hn minus 2 plus 1 plus 1. So it can be written as 2 square into Hn minus 2 plus 2 plus 1. Again, Hn minus 2 can be expressed in terms of its previous terms. So Hn minus 2 can be written as 2 into Hn minus 3 plus 1. Like that we can substitute. Finally we get 2 into n minus 1. In this way we can find solution for Tower of Hanoi problem. So all these are the Tower of Hanoi and finding rabbits, computing compound interest, all these are the some of the applications of recurrence relations. Now we will discuss about what is a linear homogeneous recurrence relation. So a linear homogeneous recurrence relation of degree k with constant coefficients is nothing but in this form. An equal r1 into an minus 1 plus r2 into an minus 2 plus and so on rk into an minus k, where r1, r2 and so on rk are real numbers are constants and rk is non-zero. So if a expression is in this form, we can say that it is a linear recurrence relation. Why it is homogeneous means if you take all these terms to left side, then we will right hand side will get to 0. That's why it is homogeneous. Here we are saying that it is of degree k because see this sequence an expressed in terms of n minus k. So what is the difference? N minus of n minus k. So we will get k. That means the given expression is expressed in terms of k terms. That's why its degree is k. So this is a linear homogeneous recurrence relation of degree k. So these are some of the examples. See one recurrence relation Pn equal 1.05 into Pn minus 1. What is the difference? N minus of n minus 1 equal to 1. That means this is a linear homogeneous recurrence relation of degree 1. See this Fn equal Fn minus 1 plus Fn minus 2. Find the difference between highest power and least power. That means n minus of n minus 2. We will get 2. Hence, Fn equal to Fn minus 1 plus Fn minus 2 is a recurrence relation of degree 2. Take this one, An equal to An minus 5. If you find the difference, we will get 5. So, it is a recurrence relation of degree 5. These are some of the examples for linear homogeneous recurrence relations. Next, we will discuss about solving linear homogeneous recurrence relation. Suppose if an equation is in this form, C1 into An plus C2 into An minus 1 plus C3 into An minus 2 equal to f of n. So, if equation is in this form, we can say that it is a linear recurrence relation of order 2 because highest order is n here, smallest order is n minus 2. Difference is 2. So, it is a linear recurrence relation of order 2. If right hand side is 0, it will be homogeneous. Otherwise, it will be non-homogeneous. Suppose if you take like this equation, C1 an plus C2 an minus 1 plus C3 into an minus 2 equal to 0. So when we want to solve it, first we have to find the roots for the equation. So characteristic equation roots for the given equation will be like this. C1 into R square plus C2 into R plus C3 equal to 0. So roots may be real and equal, or roots may be real and imaginary. No. Roots may be real and distinct. Roots may be real and equal. Roots may be imaginary. These are three possible cases. Suppose if roots are real and distinct, then say R1 and R2. Solution will be in this form. An equal some constant C1 into R1 power n plus some constant C2 into R2 power n. So when the solution is possible, if for the characteristic root we find two different roots R1 and R2, then solution will be like this. Next, if roots are real and equal, that means if both roots are same, then solution will be like this. An equal C1 plus n into C2 into R power n. So C1 plus n into C2 into R power n. So this is the solution if roots are real and equal. Third case is roots are imaginary. So if roots are imaginary, for example, roots are in the form x plus iy into x minus iy, then solution will be like this. Solution will be an equal R power n into C1 cos n theta plus C2 into sin n theta, where theta equal tan inverse of I by x. So this formula will be applicable when roots are imaginary. Next, see one problem. Find the solution for the given recurrence relation. An equal an minus 1 plus an minus 2 with a naught equal to 2 and a1 equal 7. So for this we have to find the solution. So what is the given equation? An minus an minus 1 minus 2 into an minus 2 equal to 0. Take our right hand side to left side. Then we will get an minus an minus 1 minus 2 into an minus 2 equal to 0. Here what is its order or degree? n minus 2. Difference is 2. So this is a linear recurrence relation of order 2. Then characteristic equation will start with 2 and one power will be reduced. So characteristic equation will be r square minus r minus 2 equal to 0. Here 1 minus 2. We have to get minus 1 here. So we can write as r square minus 2r plus r minus 2 equal to 0. So we will get like this. R plus 1 into r minus 2 equal to 0. R square minus 2r, okay. R square minus 2r plus r. Okay. Then we will get r equal minus 1 comma 2. So what roots we are having? Two real and distinct roots. So if roots are real and distinct, what will be the solution? We can write like this. An equal some constant c1 into minus 1 whole power n plus some constant c2 into 2 power n. Assume this as equation 1. Here some initial conditions are given, that is a naught equal to 2 and a1 equal 7. So substitute n equal to 0 and 1 here. So put n equal to 0. So anything power 0 will be 1. So c1 plus c2 equal to a naught. What is a naught? 2. So if you put n equal to 0 in first equation, we will get c1 plus c2 equal to. Similarly, put n equal to 1. Then we will get 2c2 minus c1 equal to a1. What is a1? 7. So we got two equations. c1 plus c2 equal to 2 and 2c1 minus c2 equals 7. So c1 plus c2 equal to 2 minus c1 plus 2c2 equals 7. add both sides, C1 minus C1 gets cancelled, 3C2 equal to 9 implies C2 equal to 3. When C2 equal to 3, what will be C1? 2 minus 3. So minus 1. So we got C1 equal to minus 1, C2 equal to 3. So solution will be AN equal minus 1 into minus 1 whole power n plus what is C2 here? 3. 3 into 2 power n. So this is the general solution for the given equation. In this way, we can find solution for the recurrence relation. Like this. If you solve like this, we will get the solution. So this is the solution. 3 into 2 power n, it was written in backside. So solution for this problem will be an equal 3 into 2 power n minus of 1 whole power n. So this is the solution for the recurrence relation. So far we tried for different roots. So if the equation has two real and distinct roots, that is the solution. Now see one more case. Let an equal C1 into an minus 1 plus C2 into an minus 2 is a second order linear homogeneous recurrence relation with constant coefficients. If R is a root of multiplicity 2, that means R appear 2 times, same root. So if R is a root of multiplicity 2, satisfying that equation, then solution will be like this. An equal some constant b into R power n plus some constant d into n into R power n. So see one more problem. What is the solution for the problem? An equal 6 into an minus 1 minus 9 into an minus 2 with initial conditions a naught equal to 1 and a1 equal 6. Here it is given as an minus 6 into an minus 1 plus 9 into an minus 2 equal to 0. If you take right hand side to left side, we will get like this. So characteristic equation will be r square minus 6r plus 9 equal to 0. This is nothing but r minus 3 whole square equal to 0. So r equal 3 comma 3. That means we are having same roots. So 3 is a root of multiplicity 2. So according to the formula, we can write as an equal some constant